VLSos here. This is a video lesson on slope functions as transformations. What do we mean by slope function? Well, let's graph a function first, and then we'll talk about the slope function of it. I'm graphing a parent parabola, a familiar function to work with, and we can define the function as f of x is equal to x squared. Parent quadratic. So what does it mean to have a slope function for this? It means that we would find a separate distinct function that would calculate the slope of the tangent line to this curve at any point we wished. I could analyze the tangent line slopes to get an idea of what that function would be. If I visualized a tangent line to this parabola at the vertex, the tangent line would be horizontal, and the slope of that tangent line would be 0. So the slope function to this parabola is going to have a value at 0. What's the slope of the parabola at this point when x is equal to 1? If we could visualize a tangent line grazing the curve at 1, and then we were able to find the slope of that tangent line, it would be 2. So at x is equal to 1, the value of the function is 1, and the value of the slope of the tangent line at 1 is 2. I could find other points, and if I did, I would graph the slope function as the line intersecting the origin with a slope of 2. Which means that at every point on the parabola, the slope of the tangent line is the value of the slope function at that same location. At this point at -1 on the parabola, if I drew a tangent line, I would find the slope of that tangent line to be -2. The instantaneous rate of change of a function is a function that calculates the slopes of those tangent lines. We also call that the derivative. And if f has been defined as x squared, then the function that is the IROC of f at any point is 2x. This line with the slope of 2. Now let's think of transforming this f function. I could define another function as the transformation of f. In this case, I'm going to go right by 6 by subtracting 6 from x. If the x function is a squaring function, then this new function is x minus 6 all squared. This new function, the transformation of f, I could graph. It's still going to be a parabola, but the vertex has moved over 6. That's the transformation that was made to f to get g. This is the g function, this is f, and this, the slope function of f, we could call f prime. So what's the slope function of g? G is a more sophisticated expression. Well, if I went through an analysis of finding the slopes of tangent lines to g, it would be exactly the same process of finding the slopes of the tangent lines to f, but those slopes would be located at the same places relative to g. In other words, transforming a function transforms the slope function for it in the exact same way. So if I wanted to find the instantaneous rate of change function of g, in other words, the derivative of g, then it's going to be the same derivative of the transformed f function. And we have the derivative of f being 2x, which means that I can find the derivative of g by the same transformation, subtracting 6 from x to go right by 6. The takeaway is that the behavior of a function in this case, what we care about is the behavior that we're calling rate of change. Behavior of a function gets transformed just as the function gets transformed, or in the same manner. Why do we care about this? Because finding slope functions is also called finding the derivative. Derivative is the fancy calculus word for a function that finds the slope of tangent lines to another function. And calculating derivatives can be rigorous. We have techniques. One of the connections to find derivatives of complicated functions is to understand that a complicated function is a transformation of a simpler parent function. So derivatives of complicated functions are also transformations of their simpler parent functions.